Here we go. So, electric charge. Matter is made up of atoms. If you've learned nothing in science up to this point, this. Pretty key. Okay? That atoms exist was a big deal. This is the whole point of the beginning of chemistry in grade 9. You go, I'm hoping, you're supposed to go through the history of the development of the model of the atom. Rutherford, Bohr, little J.J. Thomson. I always picture a 6-year-old physicist, little J.J. All these guys, Dalton, Democritus, ancient Greek guy, was probably the first one that said, atoms are a thing, and then everyone laughed at him, and then no one said anything for like 1,000 years. So this we've done this, yes? Last year?
Yeah, in Chem 11. Yeah, pretty sure I did that.
Okay, cool. Got to do with my grade 9s. You did a grade 11, whatever. Whatever. As long as it was done at some point in the last 4 years, I don't care what. Matter is made up of atoms. You got a nucleus in the middle. You got orbiting electrons. What can you tell me about either the nucleus or the electrons? Electrons are negatively charged. What symbol do we typically use for the electron? There's another part of the symbol. It's an E with a minus. Okay, E minus. E plus, different particle, positron. Yeah, we don't use E for proton, guys. What letter works for proton? So a nucleus contains protons. P plus. Did you just say, oh yeah? Like this was revelatory for you? Chemistry was last year, Joseph. Neutrons. Jordan, just start calling names. Garza Hill. Your caffeine is here. Go get it. Neutrons. Symbol for neutron is? With a... How do you symbolize neutrons being neutral? Hey, what? Sorry, Blake? A 0. N0 is the symbol we use for neutrons. So protons are P plus, neutrons N0, electrons are E minus. I don't think any of you had the pleasure of having me for Science 9. I love the electricity section, and we do a lot of this stuff in my grade 9 class. These things, what is true about protons and neutrons? They are both in the nucleus. Give me something else. Weight of the atom. Yes, they are responsible for the bulk of not the weight, but the mass of the atom. How are the mass of protons and neutrons related to each other? They are basically equal. Because they're not exactly equal, but the number of the difference is very, very small. Because they're made of quarks, and they're different kinds of quarks, because if I remember right, the proton is 2 ups and a down quark, and then the neutron is 2 downs and an up. I think is how it works. Don't worry about that. It's particle physics. We're not going to get into it. So they're equal in mass. How is the mass of these guys related to the mass of the electron? Blake, you said that these guys are responsible for the bulk of the mass. So that means the electron basically has to weigh nothing. There is a... this guy here is 1... I got to double check the fraction, but I'm pretty sure it's this. Don't write this down yet. That fraction, 1 over 1,836. The mass of a proton. In whatever unit it's like to say something is 1/10 something else. It's not 1/10. It's 1,836th. Very, very small. I got to double check that fraction, but I'm like 95% sure that's it. Yes. 1 over 1,836. That is the correct value. Very tiny, which makes a lot of stuff really easy to do in what we're going to look at now. So when atoms are bonded together to form solids, the electrons can be tightly bound, as in covalent solids like glass. Covalent means what? No, that's ionic. Non-metal, non-metal. A covalent solid is two nonmetals. Covalent means what's happening with the electrons? They're being shared between the nuclei of two different atoms, some like this. So they orbit both. Because they're orbiting both, you have a large positive charge here in the middle. You got a couple, the electrons are tiny and negative. They're bound fairly strongly to these things. Tightly bound to the atoms. As in covalent solids like glass. If they're tightly bound, it's hard to get rid of them. It's hard to get rid of them means that they don't flow very nicely. Objects that don't allow electricity to flow very nicely, we have a name for. Call them insulators. Do not allow electrons to flow easily. This is review, yes? Hey, what's up? She had an appointment this morning. She got out of here at like 8:15. I don't know if she's coming back. Other solids, you've got nuclei that are arranged in such a way that they allow the electrons to flow very nicely, very easily through them. These materials are going to be conductors. They allow, and typically these materials that are also conductors of electricity allow other things to conduct as well. Things like heat tend to flow well through objects that are also good conductors of electricity. Typically a good conductor is going to be what? A metal. Typically. And it's not even just covalent solids. Most covalent compounds don't allow electricity to flow very easily, which is interesting. What is the most important covalent compound on our planet? Water. What do you typically know of water? It's dangerous without electricity, which is directly counter to what I'm suggesting now. Okay? So covalent solids typically don't allow electrons to flow. And covalent compounds of all kinds typically don't allow electrons to flow nicely. But what about water? If you take deionized water, this is the water that you can, there's a big white, if you're in chemistry, big white jug of it up in the chem lab. You fill a bathtub full of that, jumped into it, and then threw a toaster in. If you throw a toaster in a bathtub, the idea is that you're probably going to get electrocuted. It's not going to go well for you. That's false, but that's okay. If it was deionized water, what would likely happen is nothing. Because it's not the water molecules themselves that are allowing electricity to flow, because they're covalent. It's all the other crap dissolved in the water that allows electricity to flow. You add a little bit of chlorine, and all of a sudden you've got a phenomenal conductor. Okay? So if it is just straight pure water, not a great conductor. Obviously, a good insulator is only going to be a good insulator if it's a good insulator relative to the amount of electricity you have present. Does that make sense? If I have a little bit of rubber and a small electric charge, it's a pretty good insulator. If I have a little bit of rubber and a lightning bolt, probably not going to do much. Okay? So the quality of an insulator is always relative to the amount of electricity that's present. Your skin's a pretty good electrical insulator until you get hit by lightning.
So are you saying that lightning will go through it anyways?
Typically, yes. Things like that have that kind of electrical strength can force their way all sorts of places. So you need to up the ante with, and typically what happens is it heats up the insulator, then the insulator explodes, and then it just keeps doing what it's going to do anyway. So if a car got hit with a bolt of lightning, typically what would happen is, if that's going to happen, the air inside the tires is going to heat up, causing the tires to rupture. Then all of a sudden the car drops to the ground. Those steel rims are just going to allow electricity to flow real nice. But yeah, it doesn't take much. So even saying things like insulators and conductors, things that you should be familiar with all the way back from middle school, there are exceptions to every rule. And even things like water's a great conductor isn't true. Water's a terrible conductor. It's the things that are dissolved in the water that are phenomenal conductors. freshwater still has stuff dissolved in it. Salt water is a phenomenal conductor, though. Don't go in the ocean during a thunderstorm. The subatomic particles like protons, electrons, and neutrons have a property known as charge. You said it already up at the top. Typically, the types of charge we have are called positive and negative. Charge is a measure. You guys know the unit of charge? Did they teach you that in science? Some of you will learn it with Harvey. Unit for charge starts with a C, named after a French guy. A coulomb. Okay, yeah, starts with a C. It's ohms. Oh no, volts. No, we'll get there. Charge is measured in units of coulombs. How many coulombs of charge are present? That is the amount of charge that is there. Charge is represented by the letter Q. Big or little? Because C is the speed of light. We reserve it. Nothing is C. Sorry? Capital C is how we abbreviate coulombs. Like one big C is 1 coulomb, which is a representative of the value Q, variable for charge. 1 Q, 1 amount of charge, like we say a proton is 1. This is back in the day before they were actually able to figure these things out. So like, yeah, a proton, we'll call that 1. Electron, we'll call that -1. It'll be great. But that's not actually reflective of the amount of charge that's present, because the amount of charge is determined by what makes up the protons and the electrons, which is a combination of things called quarks. 1 Q. Does anyone know what the number is? How many coulombs is present there? It's really tiny. 1.6 times 10 to the negative 19 coulombs. Very small. No, Q is the amount of charge. So one charged object, like 1 proton would be 1 Q, is equal to 1.6 times 10 to the negative 19 coulombs. So when the amount of charge.
So 2 coulombs is double that.
Charge is represented by Q. So if I have 1 charged object, like the amount of charge, so like yeah. Okay. Flip the page. Important fact about charge is that it is quantized. That might not seem profound to you, but it is. It means that there is a smallest amount of charge that is present. Another way to think of it, for those of you who are mathematically inclined, is to suggest that charge is discrete. It is not a sliding scale of charge. Okay? Charge comes in packets of 1.6 times 10 to the negative 19 coulombs. And so you can only have multiples of that number being the charge you have present. Makes sense, yes? We can accept that? So then to figure out what's going on here, the smallest unit is, well, we'll say little e is, there's all sorts of letters here. 1.6 times 10 to the negative 19, so we've got an electron, that's coulombs. All charges are multiples of E. So the total number of charge Q is equal to N, your number of charges, an integer, times E, the elementary charge. Hey, Don, what's up? No worries, that's fine. I don't have black, but I have the piping at the back. Are you talking about backdrops for a stuff we use at Storm the Wall, and it wasn't black? So if we are desperate for black, we have to either buy some or we just use the rolly things that are in front of Chef's little house. Okay, no worries. But Steph, if you want, the boxes at the back are all my, ignore the piping, but the boxes beneath the piping are all of my supplies for that booth. I don't know if you want it now, the top, or you can grab it later. Either one. Technical comment here. There are particles called quarks. Quarks are what are responsible for giving charge to things. One kind of quark is actually 2/3 E. One other kind of quark is 1/3 E. So E is not the actually absolute smallest charge. They just thought it was. This is the charge on an electron. But like, actually, these things are made of smaller things. So rather than change this number to reflect the charge of one quark, they said, well, there's just, there's two of this and one of those. So we'll just call that 2/3 E and 1/3 E, and we'll call it good. Because why break 200 years of physics when fractions exist? It was basically what the particle physicists did. Okay? So there are quarks that do this. We're going to ignore them because we can. So something simple like find the number of fundamental charges in a particle of charge 2.5. That symbol, we know what that symbol means, yes? That looks like mu. But in this context, we no longer use it to represent the coefficient of friction. Okay, we need some things here. Yes, it is still the Greek letter mu. No, I'm so sorry. Okay, so back to, let's wind it back a little bit. Go to the metric system. Metric system is beautiful because the metric system is all multiples of 10. Okay, so if my base unit is meters, which I'm not going to write down, a centimeter is how much of something? No. A single centimeter is 1/100th. Okay, so a centimeter, if meters are my base unit, a centimeter, C, represents 10 to the negative 2 of something. A millimeter, that M represents how much of something? 10 to the negative 3. We don't like 10 to the negative 4. We don't like 10 to the negative 5. They're useless. Why carry them around? But we do like 10 to the negative 6 of something. 10 to the negative 6 is micro. So if you wanted a micrometer, micro starts with M, but we can't use M because we already used M. So let's just jump over to the Greek alphabet, use the Greek version of the letter M. Greek version of the letter M is mu. So when mu is connected to a unit, it represents a micro amount of that unit. So 10 to the negative 6 of something. So if I have 2.5 microcoulombs is how I would read this. This is 2.5 times 10 to the negative 6 coulombs. And that's going to equal some number, n, times the elementary charge, 1.6 times 10 to the negative 19. Coulombs. So what's 2.5 times 10 to the negative 6 divided by 1.6 times 10 to the negative 19? That's going to give us our value for n. Into the 13. And we know what kind of particle that has to be because we were told that originally they said 2.5 microcoulombs. There is no negative in front of it, so the implication is that this is positive. So I have 1.56 times 10 to the 13. What kind of particle? It's positive. So the positive elementary charge is a proton. Cool, yes? Relatively straightforward? Comments, questions, concerns? Okay, I'm going to go back over here. Don't flip yet. We're going to look at the metric system a little bit more. There's one more that is nice. We don't like 7, we don't like 8, but we do like 9. 10 to the negative 9. You read that as nano. And nano is what you would expect. Nano is the little letter n. So if this was NC, that would be a nanocoulomb times 10 to the negative 9 coulombs. Mu C is micro. It could be little mc is millicoulomb. A millicoulomb charge. Now you're dealing with, that's actually a fairly large charge, all things considered. Now we can flip if we're cool with all this. These are things, these guys you're going to want to have handy. Milli, micro, and nano. are things either remember them or, you know, toss them somewhere useful. So instead of an electron being worth 1 positive charge and a proton, sorry, -1 positive charge, and a proton being worth +1 positive charge, we've got a charge on electron being -1.6 times 10 to the -19 coulombs, and a proton being +1.6 times 10 to the -19 coulombs, and a neutron actually is 0, just the way the quarks line up. You can see here the mass of the proton and the mass of the neutron are different, but like not much. When you're dealing with 0.01 times 10 to the -27, they're that's basically the same thing. Which is why we assume them to be the same thing when we're dealing with chemistry at the level that you've been dealing with chemistry for. All of these values, if I'm not mistaken, are located on your formula sheet right here. This, I'm going to I'm going to box this off. Okay. All of this stuff are your constants that are necessary for gravitation. The stuff up here. This box that I have isolated, Ke, proton mass, neutron mass, electron mass, and mu sub 0. Mu is going to mean something else. There's 3 things for mu. Sorry, not my fault. This is all E and M. E and M stands for electricity and magnetism. Okay, so if you're looking for a constant related to electricity and magnetism, this section of your formula sheet, your data chart, is what's going to be where things are going to be useful. Cool? So we're going to refer to that. Stay. Some other extra bonus things, because this curriculum has changed so much. It used to be in Science 10, then it moved to Science 9. Now maybe you only do it in Chem 11. Do you guys talk about alpha particles? Radiation? Have you talked about radiation in science at all? Some of you are nodding, some of you are shaking your head. So there's going to be language that gets thrown around here. They're going to be like, oh, yes, an alpha particle, or oh, yes, a beta particle. Just so you're aware of what the language is. That's symbol alpha. This is an alpha particle. The reason it is useful is because it is a charged particle that is emitted by some radioactive processes. So it's going to show up here when we talk about E and M. An alpha particle is a helium nucleus. If they didn't know that at the time. This was connected to Rutherford way back in the day. Alpha particles, helium nucleus. It's just the nucleus. This is 2 protons and 2 neutrons. There's also beta particles. That might show up as well. Beta particle is just an electron. So if you ever hear something, if we're talking about alpha radiation, it's helium nuclei. If it's beta radiation or a beta particle, it's emitting electrons. E minus. So this particular question says, what is the charge on a helium nucleus, an alpha particle? So I want the charge Q. It's going to equal N times the elementary charge. What part of the helium nucleus is going to provide us with that charge? Protons are what's going to provide us with the charge because neutrons are neutral. There are 2 of them, and each one of them has a charge of positive 1.6 times 10 to the -19. So the charge Q on one alpha particle helium nucleus is what? You should not need a calculator for this. Thank you, Joseph. 3.2 times 10 to the negative 19 coulombs. New but not earth-shattering, yeah? Okay, that's the page. So, if we were doing an electricity or magnetism experiment on a piece of matter, then we should note that it is only the electrons, you should know this, it's only the electrons that move, yes? Protons are locked in. If the protons moved, for example, if I had a metal bar and the protons were moving, that would start to deform the metal bar. That means the entire atom is now shifting, and so you're warping the whole bar. Reality doesn't warp like that. So the only part of a particle rather that flows are the electrons. That should not be earth-shattering to you. So we're gonna draw lots of these kinds of diagrams over this chapter. For a conductor, electrons flow easily. Insulators, they don't. Electron orbits can shift slightly, though, and even in an insulator. Those of you who take chemistry know this. You can have partial positives and partial negatives. We talked about this. In covalent compounds, like water bonding, you can talk about hydrogen bonds. So hydrogen bonds, how do hydrogen bonds work? Come on, chemistry students. This is Chem 11. How? Oh my gosh. Oh my gosh. Okay, here we go. Okay, we'll do it anyway. So you've got, you're cool with the fact that water can, yes? Okay, so they're sharing electrons. He's got a pair, and then there's being shared here and here. Okay? You looked at a concept called electronegativity, yeah? So I can see a couple heads nodding. Was this Chem 11 or Chem 12? Easton has posters of this one. Okay. Never mind. Forget that part. Let's just say that these guys are sharing electrons. It's not quite equal because there's a property. That's what I'm looking. There's a property of oxygen and a property of hydrogen. Oxygen has a higher electronegativity, which means yes, they're sharing, but oxygen is sharing closer to itself. You can look, but you cannot touch. We're sharing, but we're not sharing. So the way hydrogen bonds form is that you get another water molecule comes in here, and this guy, because he has a higher electronegativity, these electrons are slightly closer to this guy here. This guy's positive here. So on the oxygen is not, it's not an ionic, where the oxygen is like, no, these are mine, and I'm going home and take my electrons away. So it's not, oxygen doesn't have a charge of -2, but it is more negative, because there's chemistry lesson, there's 6 protons there, and now there's 8 electrons that are pretty close to this oxygen. So we're cool with the fact that oxygen is slightly negative, but it's not. So we say that this thing has a partial negative charge. Well, this water is doing exactly the same thing. The electrons that are being shared, quote unquote, are mostly near this oxygen. So that means the hydrogen isn't like totally positive, but it's pretty positive. So the partial negative and this partial positive here are what attract each other in a hydrogen bond. Screen any bells. Please nod aggressively if you're like, yes, I've heard this before. Shake your head vigorously if this is totally new to you. Okay, so it's you. Are we cool with the idea though? Okay, you have a partial negative and a partial positive based on a property of atoms called electronegativity. You can accept this to be true even if this is new. Okay, so this whole thing, water, we say as a molecule, is neutral. Okay? Because they're sharing all the things between them. Yes, he's partially positive. Yes, he's partially negative. But that partial positive and that partial negative cancel each other out. We say water is neutral. You don't walk up to water and get shocked by it. This process, though, the fact that the electrons can shift slightly is called ionization. Which I used before? Yes. No. Polarization. Yes, polarization. Not ionization. It's polarization. Sorry, my apologies. Okay. Which is why we say things like, if you've ever heard the language, water is a polar molecule. Those of you chemists, have you heard this before? Polarity. This is why. Because the electrostatics of it all interact with the chemistry of it all to combine to make life happen. So we've got this idea of polarization. It's not positive, it's not negative, it's neutral, but the positives are hanging out over there and the negatives are kind of hanging out over here. Cool with this? And for those of you calculate, never mind. No. For this calculus involved there too, but I'll ignore it. Okay, so polarization looks like this. So we're going to draw a bunch of protons. The protons, though, do not shift. And we're going to demonstrate that in this diagram by drawing protons in the exact same location in all of our objects. Okay, so let's say that there are going to be 6 protons in the bar, just for fun. 1, 2, 4, 5, 6. So all these bars need to have the protons drawn in basically the exact same location, because they do not move. And we're just going to say that this little ball hanging here on a stick has 1 proton in it. The insulating ball here, they don't tell us the charge in it, so we're going to assume that the charge on the insulating ball is neutral. If the insulating ball is neutral, what do you know about the electrons in the ball? Equal to the number of protons. And how many protons did I draw? No, in the ball, not the bar, the ball. 1. I drew 1 there, so we're going to toss 1 electron on each ball. I'm going to use pink so it stands out a little bit more. I'm going to zoom this in so you guys can actually see my graphic a little better. Focus it. Cool, thank you. So we're going to draw a negative on each one of these balls. It's an insulating ball, so the electrons aren't going to flow in and around the ball, well, in the ball themselves. But we've got this negative rod. So we don't know anything about the properties of the rod, but it's going to be it's negative. So if it's negative, what does that tell us about the relationship between the protons and the electrons? More electrons, and it's negative, so we're just going to load this sucker up. Here we go. Nope, stop. Negative. And they're going to repel each other, so we're going to distribute them relatively evenly over the thing. Bless you. Oh, I drew something I shouldn't have drawn. That's okay. So we've got our real negative thing, and I got a neutral thing. What happens with a neutral object and a negatively charged object? What do they do? That is not true. What does that little sound effect represent, Zach? They attract each other. Okay? So, maybe I have to write that down here. Positives attract negatives. So positives and negatives attract each other. Both of these guys attract neutrals. So if you have a neutral charge, positive attract negatives, positives and positives repel, negative and negative repels. 2 neutrals don't do anything, but positives and negatives both attract neutrals. So I've got this guy here. There is going to be an attractive force, electric force, of attraction here. So what's going to happen? That little ball is going to swing towards it. as this ball swings towards this very negatively charged object, this is an insulating ball, so the electrons can't flow per se, but they can shift in their location. So what actually ends up happening is that this electron that was located here is going to shift to this side, so that this object here is going to have a partial positive on the left side and a partially negative charge on the right-hand side, even though that object as a whole is still neutrally charged. Nathan, am I losing you? You just tired? That's how, no, it's, sorry. This is, sorry, yes. If there are things that I'm assuming you understand from chemistry and you don't, please say something. This shows up in chemistry. Should show up in chemistry. The idea of a partial positive and a partial negative. This D gets thrown around sometimes in chemistry. It's actually connected to a partial derivative in calculus. Yeah, you're never going to get away from calculus nowadays. So what happens, because you got a partial positive on the left-hand side and a partial negative, we know that positives attract negatives. So we got a positively charged, quote-unquote charged, left-hand side of this insulating object, and a whole ton of negatives on here. So these negatives are going to repel each other and are going to be attracted to this guy here. So these negatives, because they're in this negative rod, can move as well. So you're going to get a buildup of negatives on the right-hand side here, where they were uniformly distributed before. Because we brought the partially positive pith ball over, or the insulating ball over, the electrons are going to shift. The electrons, some of them, not all of them, some of them are going to actually end up jumping over onto this insulator. But they're insulators, so once they're there, they're stuck. So what's going to end up happening then is we've got not all of them jumped, so we've still got a negatively charged rod. But because a bunch of these guys jumped over, now that insulating ball has what charge? It was neutral, now it's negative. So now we've got a negative rod and a negatively charged insulating ball. So now they repel. Looking at the properties of insulators and conductors. And introducing you guys to some new notation and perhaps reviewing some chemistry. This is connected to this phenomena here called polarity. And life doesn't happen on our planet if polarity is not a thing, because no polarity, no water. Okay, flip the page. Let's do another example. This is called an electroscope. Something else, sorry. No, we're good. Okay. So, electroscope looks like this. It's a flask, sometimes it's a little box. It's got a little metal rod on top, sorry, a little metal ball, and a rod inside here. You know what? Rather than draw the picture, let's just show you one. Let's try this one. You guys don't need the bonus music. The music is weird. Okay, so this is an electroscope. See, you got your box. You got the little metal disc on top. This is made of plastic or rubber, important because you want to insulate the metal rod inside this thing down here at the bottom. Now this thing here at the bottom, you've got a piece of gold foil. Typically it's gold because gold's strong and light, relatively speaking. Like you can pound it really thin, have a pretty light gold foil sheet. And this is the part of the metal rod connected to this guy up here. What's going to happen is they brought a charged insulating rod. So they imparted a charge on this guy here, brought him close, and then this guy stands up. They take it away, it goes away. Bring it close, it moves up. Like magic. But then they should touch. Do they touch? Oh, no, they don't touch. Come on, touch. Bring it close. Oh, they're going to touch it. What happened? Skin's an insulator, so the skin stopped something. So what happened? Okay, so we're going to go back here a sec. Let's look at what happened. Okay, so what's happening here? Okay, so does anyone want to take a stab at explaining what's happening here? I'll tell you now that this rod is negatively charged. And that this is a metal conductor, and that's gold. They don't take a guess, make an attempt at explaining what's happening here. Well, at the beginning, it's just hanging there. Like there's nothing going on there. It's not attracted to anything. Its own mass is holding it down against the bar. So this whole setup starts neutral. So we have the negatives here, and this whole thing is neutral. Neutral means what? It means no charge. It also means what? What's balanced? The electrons and protons are balanced. Okay, so you've got a uniform distribution of protons and electrons inside this thing, and this thing is negatively charged. It means this thing has an excess of negative charges. Okay, so as it's brought close, without touching, what's happening? There's nothing being transferred. There's no sparks. Nothing being transferred. What's happening? Sorry? How? Over, sorry? If you see electrons moving, you should be seeing sparks. We don't see a spark, therefore there is no electrons moving. So this thing is... Positives can't move. Protons cannot move. This thing's negatively charged. So you got a buildup of negatives here. Sorry, Abigail, you had a thought? Which rod? When you say rod, what do you mean? This thing here? So this thing comes close. There's a lot of negative here. Yeah, keep talking. Yeah, the electrons in the disk are repelled by the electrons in the charge. So they're moving down. Everything here they're all technically neutral. So the gold's just hanging here. Oop. Just hanging here. So neutral means there's a uniform distribution of electrons. Abigail said this is negative. That means this is going to then repel the electrons that were in the disk. This bar goes through this plastic insulator, so they're going to flow down the electrons here. Keep talking, Abigail. The gold was neutral. The electrons that were flowing down away from this disk, some go down here, some go onto the foil. And then they repel each other. Well, as soon as the rod leaves, there's no repulsive force up here, but there's a large repulsive force on all the electrons that are built up down here. So they redistribute themselves so that when this thing gets pulled away, they flow back to where they were. So this whole thing is equally neutral. So then the gold foil can just fall back down. So let's look at what's happening here. It doesn't. There have to be electrons in it for it to have no charge, because it has protons. It has to have the same number of protons as electrons. Yeah. Okay, so let's look at what's happening here. Okay. Now, where's the finger? Okay. So it looks like the finger is touching, but the finger is not touching. Looks like the rod is touching the finger's touching the disc. That's not what's happening. The finger's touching the disc, the rod's just still close. So what's happening here? Nate? And so, sorry, to go back to Abigail, everything you said, totally correct. Okay? So operating under the assumption that everything Abigail said was correct, what's happening now? This thing drove all of the electrons in the disk, well, a majority of the electrons in the disk, down to the foil here. There's no flow. This is where things are getting weird, because the finger is causing something weird here. What's going on? Oh, well, maybe that's true. Let's look at what happens then. So as soon as the finger and the rod are both gone. And now the foil stands up. So now with no rod present, there has to be a charge present.
Because only electrons can move, so the finger took some of the electrons.
So the finger had to have taken some of those electrons. So what happens here is, yes, the finger's present. This thing is driving the electrons out of the disk. So the electrons actually just jump onto the person. Sorry? But you can still build up charge on an insulator. This is why as a kid I would walk around Costco, drag my feet, and grab my mom's hand. Bang! She would freak out every time. It was great. Okay? You can build up charge on an insulator. So even though the skin is a good insulator, you can build up charge on it. So if this guy comes close and you've got a whole bunch of electrons repelling each other, the finger's acting as a ground, basically. So that nothing weird is happening down here. The electrons are just getting piled up here. So that when everything gets pulled away, you're left with a positive charge here because there is a deficit of electrons in the system. So now what's happening as you, hold on here, where did it go? Where did it go? Oh, it was like right here. Because now they brought the, did I skip too far ahead? Let's go back here. Okay, yeah. Let's go back here. So now you've got a positive, partial positive here and here, because there's not enough electrons in the system to uniformly distribute to make the whole thing negative. But when they bring the negative rod back, oh, dang it. You saw the gold foil flip down. What happened there? The negative rod forced all the electrons up here. It's back down here. At that point, these two things became neutral. The diagram that I have on the page that we're going to draw all this happening, doesn't have this whole last second step here. But that's what's going on. Cool? Sorry? Why there dislikes? I don't know why there's dislikes on the video. Probably the music. I didn't like the music either. It was like big band. I muted it. Okay, so let's draw what just happened. Without the rod, this system is neutral. Neutral system means equal amounts of positives and negatives distributed uniformly throughout. So let's draw that. Positive, pause 2, 3, 4, 5, 6, 7, 8, 9, 10. The positives were going to stay in the same spot on all of these things, so we can just draw them all again. 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this, I'm not going to draw the positives in the rod up at the top because they're not necessary. All you need to know is that the rod is negative. So we're going to bring a whole bunch of negative charges on the end of this rod are going to come close to this electroscope. At this stage, where are the electrons? They are evenly distributed throughout the system. So I'm going to pair an electron here with every proton. Negative, 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 negative. When this large negative charge on the rod comes close, what's going to happen? It's going to drive all of these electrons, because these electrons are going to be repelled by this guy. It's going to force all of these electrons to shift down here. Now, this whole object is still neutral. Sorry, this shall be negatives. They're pink. The pink stuff. Sorry. The pink things are all supposed to be negatives. So while this object is still neutral, there is a partial positive charge here and a partial negative here and here. And it's these partial negatives that push each other away on those leaves at the bottom. When you take the negative rod away, that allows these guys to redistribute. Negative, 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 negative. Throughout the system. So you can't see them, but there's got to be something moving around in there. And relatively quickly. There wasn't a lot of delay. Comments, questions, concerns? We've seen stuff like this before, or is this all new? Toby, you're not sure? Okay. Okay. Well, and this is the kind of stuff, if you went to Science World, you'd see stuff like this, be like, oh, neat, but you would never really get an explanation of what's going on in the background. This is what's going on in the background. Let it go, man. Let it go.
We come back for our 5-year review. We get the whole stronger goal.
Okay, we're going to skip this example for a sec because I'm going to go try it and go upstairs to grab a Van de Graaff generator to actually do this one if we have the materials for it. We used to. If I can find them, we'll do it. No, but I want the pie plates as well. If everything's up there, I'm going to do this example with you guys. Okay, but just because they're there doesn't mean they work well. They're finicky pieces of equipment. They fail sometimes. No, the Van de Graaff generator is finicky, Nathan. Here we go. I want you guys to play with these. Couple, just playing around with charges. I want you to do 1, A to C. I want you to do 2, A to C. Yeah, that's great. It's there, but my hand's in the way. Just wait. 3, 4. No, it's not enough. 6 and 8. Oh, no. Nine is the first is a connection between the circular motion stuff and electrostatics. Take a look at 9 real quick. Actually, I'll just throw it up here. 9's a beautiful question. In an atom of hydrogen, an inwards force of 8.2 times 10 to the negative 8 newtons acts on an electron. We'll figure out how to calculate that force shortly. The electron is moving at an approximate 2.2 times 10 to the 6 meters per second. What is the approximate radius of the electron orbit? So what you're going to do here is basically you're finding the size of an atom of hydrogen, which is pretty cool, using uniform circular motion. That's what you're finding. That's the question. The question says, what is the radius of the electron orbit? They tell you what F is. You know what B is. So it's a really easy connection of uniform circular motion and electrostatics. And technically it's not uniform because electrons do weird things around an atom, but for all intents and purposes, that's what we're dealing with. Okay, give those a shot. I'm going to go upstairs and see if I can grab a Van de Graaff generator.